Okay, this is part 2 of the video for the section entitled The Identity and Inverse Matrices. We are looking at these two matrices, R and S, and we're being asked the question, are these two matrices inverse matrices? Well, in order for two matrices to be inverses, A times B has to equal the identity matrix, and B times A equals the identity matrix. So in this particular problem, we have to show two things in order to show that R and S are inverses. First, we have to show that R times S is the 2 by 2 identity matrix, which would be 1, 0, 0, 1. Then we have to show that S times R is the 2 by 2 identity matrix. Now, if at any point in time any entry in that problem does not match the identity matrix, the problem would be over and the answer would be no. Most common question I get is, what if we have a negative 1? Negative 1 is not equal to 1. So that would be a no, and the problem would be over. So, if we want to show that R and S are inverse matrices, the first step in that process is to check that R times S is equal to the identity matrix. So we start off and we say, okay, R times S. So that would be matrix R, which is 2, 2, 3, 4, times matrix S, which is 2, negative 1, negative 3 halves, 1. Now we all should be relatively familiar with this process by now. We are going to do row 1 of matrix R times column 1 of matrix S. So that would be 2 times 2 plus 2 times negative 3 halves. Now, it is worth noting that we should check as we go to make sure that each entry here matches the identity matrix. That is 4 plus negative 3, which would be 1. That's what we're trying to show, so we continue. So then, that was the yellow here, we would do row 1 times column 2. It's going to be written right here. So that's 2 times negative 1 plus 2 times 1. Now that has to equal 0. Well, 2 times negative 1 is negative 2. 2 times 1 is positive 2, so negative 2 plus 2 would be 0, and we would continue the problem. So now we're going to go down to row 2. We're going to do row 2 times column 1. So that would be 3 times 2 plus 4 times negative 3 halves. And again, that has to equal 0, which that would be 6 minus 6, which would be 0. So we would continue. And we would show that row 2 times column 1 was equal to 1. So that's 3 times negative 1 plus 4 times 1. That's negative 3 plus 4, which is 1. So at this point, we have absolutely shown, without a doubt, that R times S is equal to I. So then we move to the second half of the problem, because that is not enough to declare them inverses. We still have to check and make sure that S times R is equal to I. Now you might be thinking, gee, that sounds like it's exactly the same, but it's not. Matrix multiplication is not commutative. R times S is not the same as S times R. So we would take those matrices and we would switch them to negative 1, negative 3 halves, 1. And we're going to multiply that by R, which is 2, 2, 3, 4. Now, though that process is extremely similar, it is not going to result in exactly the same answers. So again, we're trying to show that that is the identity matrix. So we start off and we say, okay, we're using the rows from S and the columns from R. So we're doing 2 times 2 plus negative 1 times 3. That would equal 1, so we would continue. So then we would do row 1 times column 2, which would be 2 times 2 plus negative 1 times 4, which would be 0. Then we have row 2 times column 1. That is negative 3 halves times 2 plus 1 times 3. That would be negative 3 plus 3, which would be the 0 that we require. I missed one of my colors here, so let me get that fixed. There we go. And then finally, row 2 times column 2, which would be negative 3 halves times 2 plus 1 times 4. It's negative 3 plus 4, which is positive 1. So once again, we have shown S times R is equal to I. So our answer here would be yes, R and S are inverse matrices. So we would say yes, R and S are inverse matrices. And again, the only reason we can state that is because we have shown the work to show that R times S is equal to I and S times R is equal to I. Let's do another one. So here we have matrices C and D. Same thing, we're going to have to show that C times D is equal to the identity matrix, which in this case is again a 2 by 2. And then we have to show that D times C is equal to the identity matrix. Same identity matrix. So we start off with that first step. We're going to show C times D is equal to I. So we have C times D. C is 1, 5, 1, negative 2. Multiplying that times D, which is 2 sevenths, 5 sevenths, 1 seventh, 1 seventh. So we start off and we go to row 1 of C times column 1 of D. That is 1 times 2 sevenths plus 5 times 1 seventh. And that has to equal 1. Well, that's 2 sevenths plus 5 sevenths, which would be 7 sevenths, or 1. So that does work. And we continue to the next entry, which is row 1 times column 2. That would be 1 times 5 sevenths plus 5 times 1 seventh. Well, that has to equal 0, but that's 5 sevenths plus 5 sevenths, which would be 10 sevenths. So right there we can stop. Okay, the second that this is not a 0, we are done with this problem. Because right there we have had a problem. C times D does not equal I, which means no. C and D are not inverse matrices. The second that we run into one entry in this problem that does not match the identity matrix, that is the end of that problem. I will do an additional video that shows the example for the 3 by 3. I'm doing that because there is a bonus question on the homework for that approach, but it is exactly the same approach. We would have to show that one times the other is the identity matrix and vice versa. So that's it for this video.